Thank you very much. So I have an hour here with you. I have a captive audience. It's an honor to be speaking in front of this auspicious group. It's been a decade since I've had the opportunity to do that. Marianne asked me to give this talk, and I said, well, what exactly do you want me to talk about? And she said, well, you know, talk about your science and talk about how the CSGF affected your life and your career and how it still does that. And so this is going to be sort of all over the place. There is a progression to it, but we're going to go on some little asides. And I have the challenge of keeping you all awake, because you all have just eaten. So we'll see if I can do that. Of course, most of this work is all collaborative, so I've got a host of people I need to thank, or at least take credit for. I do really like the Scott Adams quote. It is a lot faster to take credit for other people's work. You might notice that there's another CSGF folk up here. Dan, hopefully he's out there somewhere. Margaret reminded me yesterday that there's a lot of my own opinions in this, so I'm going to put a disclaimer up here. I'm not representing anyone but myself. My wife would be, you know, very adamant about that. So you know, take what I would say with a grain of salt, maybe. All right, at any rate, why fusion? Of course, as we all know, energy is a big issue right now, right? And there are a lot of different ways we might go about solving the energy problem. And I think we should be pursuing all of them, because I think ultimately we're going to have some kind of heterogeneous mix, right? But fusion is a very interesting one. Unlike nuclear fission, it's got a lot of advantages. Operationally, the fuel is very abundant, not nearly as rare as something like uranium. There's less severe accident potential. These devices don't actually run in some mode where you could have some critical runaway of a reaction, right? Basically, if you don't keep pumping stuff into the machine, it just shuts down and stops. So that's a very nice fail-safe mechanism. They're a steady source. When operated in a steady state mode, unlike, say, wind or sun, when you can't quite control when things are going to be blowing or whether the sun is going to be shining or whether it's going to be cloudy that day, that's a really big challenge for the power industry, because they really like a steady input into their power grid. They don't like something that's fluctuating all over the place. So that's another good advantage here. Environmentally, the radioactivity of the things you produce from one of these devices is measured in half-lives of tens or hundreds of years, not tens of thousands of years. So the whole issue of waste is a much easier issue to tackle. Low carbon footprint, I won't say it's zero carbon, that's not really true. You have to build these devices, right? But in an operational mode, you're not generating more carbon. Low land usage, watts per square foot. You can get a lot more power out of a fusion power, well, in theory, you can get a lot more power out of a fusion power plant than you would with a field full of solar arrays or a wind farm. And security advantages, because they're not this big, scary, radioactive source. I mean, they are a radioactive source, but they're not, really scary like a dirty bomb. It's a less attractive terrorist target, and you're not really generating some of those materials, the special nuclear materials that might be relevant for a nuclear program. So it helps with the proliferation issue as well. So what is fusion? So my kids love They Might Be Giants. And I don't know if you know this, but they actually have a kids album, and they have a little short one called Why Does the Sun Shine? And on Why Does the Sun Shine, they have this song. And the lyric is, the sun is a mass of incandescent gas, a gigantic nuclear furnace, where hydrogen is built into helium at a temperature of millions of degrees. And that's actually really accurate. That's pretty good for a couple of musicians, right? That's true. The reaction that we're really interested in here is you take deuterium, you take tritium, you hold them together at a really high temperature, long enough, you have a fusion reaction, out pops helium, neutron, and energy. And you get the energy because of E equals mc squared. There's a little bit less mass that comes out the other side, so some of that mass is converted to energy. This isn't actually the reaction of the sun, but this is a reaction that we actually can get the most out of here on Earth. Of course, we can't build a sun here on Earth. That would be bad. So what are the main approaches? I'm going to talk about two, primarily because those are the two I work on. So I'm not qualified to talk about the other ones. There are other methods such as Z-pinch or inertial electrostatic confinement. But the key here is you need to confine the fusion reaction, right? And the sun does that with gravity. We can't do that. The two key ways of doing it are using magnetic fields. You create some magnetic fields that hold everything together and squeeze it together. Or you use the inertial confinement, which is a little trickier. What you do is you have a target, and if you irradiate the outside of that target, it'll ablate and ionize. And all of that ionized plasma that comes blowing off of there has an equal and opposite reaction. It sends a compression wave into the target, and that thing will compress down. You get it down small enough, you get it symmetric. You'll get temperatures and densities that are high enough that you actually get the fusion reaction to start. So those are the two methods that are sort of the standard approaches that people are pursuing. Now the joke, well, this is a version of the joke, fusion is only 20 years away, and it always will be. It's kind of like when you're like trying to finish your degree. You know, when are you going to be done? 6 months. 6 months. I think I said that for 3 years. That's cute, but that's actually not very true. This is a really hard problem because you have to deal with some really complicated physics. And despite that, the fusion community has actually been making a lot of really impressive progress. When you look at the tokamaks, where they start, you know, if you look from 75 on, you've got, you know, a 1,000-fold increase here. If you actually calculate it out, this is actually faster than Moore's law. And you're getting up around, you know, these Q numbers here, those are the break-evens. A Q of 1 is you're getting out as much energy as you're putting in. So, you know, they're very close to actually getting more energy out at this point. Similarly, on the ICF side, there's been steady progress in creating lasers that can produce more and more and more energy. And you know, now we have NIF, and it's right at the level where in 1972 it was predicted that you would need to get to if you wanted to actually have inertial confinement fusion. So progress has actually been pretty steady. I mean, you can see that. It's not like the communities have been struggling and not getting anywhere. In fact, there are two major devices coming online very soon. So ITER, you may have heard about ITER. This is an international collaboration. It's being built right now in Cadarache, France. This is going to be this massive tokamak. Okay? This is a magnetically confined device. If you look, that little thing right there, that's a person. All right? This has a plasma volume, so this inside here is about 840 cubic meters, which is, I don't know, it's like a 200,000-gallon swimming pool or something like that. That's a lot of volume. It's going to take 50 megawatts in. So if you remember yesterday we were talking about 20 megawatt machines. So this is going to take 50 megawatts in. It's projected to generate 500 megawatts plus. Each burn cycle will be on the order of minutes, which is a relatively long time for them. And they're expecting this 10-time factor of gain. So they're shooting for 2015. That probably won't happen because, well, budgets aren't great anywhere right now, right? So everything keeps getting pushed back. On the ICF side, we have the National Ignition Facility, which is actually built. It is built, it is operational, and they are currently working on the sequence of experiments that they need to do to achieve fusion. It's pretty impressive. You got this massive building with this massive sphere on the inside with 192 lasers all focusing down. So there's that person, there's the person again. It's focusing down onto something on the end here that's that, okay, which is like that big. It's a 2 megajoule laser. It'll put 500 terawatts of power into that spot over about something on the order of nanoseconds. And they're expecting a 10 to 20 time gain, and they're ramping up to that. I actually haven't worked directly on NIF in a couple of years, but the latest I got from some of the people who work there was that they already have produced a neutron flux that's an order of magnitude higher than they have on any of the other ICF devices. And I think they need to get another order of magnitude until they declare that that's actually fusion. So that's moving right along. Why is fusion so hard? Well, to understand fusion, if you get fusion to work, you really have to understand plasmas. So any biologists out there? Not that kind of plasma. So the plasma here, we're talking about a cloud of ions and electrons that are interpenetrating and interacting, okay? And plasmas are way cool because they do so many weird things. But for instance, in the ICF application, you've got this whole realm. You're shooting all these lasers in, You get a temperature of millions of degrees on the inside of this tiny little canister. All the materials in there start to ablate and ionize. You get this plasma that's formed. And the plasma starts to interact with the lasers because you have these charged particles that are moving. Those generate electromagnetic fields. The laser is an electromagnetic field, and particles in an electromagnetic field respond to that. So you have these really interesting couplings that happen. So really, to get the whole fusion thing to work, you have to really get the handle on the plasma physics and what's going on. And one aspect of that, there's certainly some hydrodynamic type aspects of that, of stabilities that you need to get symmetry. But the part that I'm really interested in, that I think is way cool, is the way that the lasers actually, for instance, in ICF, interact with the plasma. So for instance, there's this inverse Bremsstrahlung process where an accelerating particle can actually absorb a photon. And that takes energy out of your laser beam, and so you don't get the energy where you want it to go. You have these couplings where if you have a suitable flow, suitable conditions, cross laser beams and air won't interact with each other. It's all a linear process. They go right through. If you're in a plasma, the plasma can actually couple the two beams together. What happens is the energy flows, instead of continuing on, you can actually get it reflected or shot into the other beam. You get a resonance that sets up and it actually reflects energy from one beam into the other beam. Lasers can kind of dig their way through a plasma. As it propagates through, there's a ponderomotive force. There's this force that the laser pushes on the electrons and pushes them out of the way. It's like a snowplow. So all that plasma moves out of the way. But now we know what light does when you have different density areas, right? Index of refraction. The light's going to want to go into an area that has less density. So once you've pushed stuff out of the way, the light starts to focus down. And this can lead to some really interesting filamentation instabilities. And probably the one that's most of concern for NIF are these laser-driven resonances, where you'll get these multiple waves that set up where the laser propagating in will actually drive a density wave inside the plasma. And once you get that density wave set up, it's of the right frequency because it's near a resonance. That density will actually reflect the energy off into a different direction. Now that's critical because with these ICF applications, you're trying to put energy in a very specific place. And any of these mechanisms are going to serve to put the energy somewhere else. All right, now I'm going to change topics. We'll get back to that. But I thought this was an interesting time to kind of jump into something else. What are you? So I actually had to give a talk on some of this work, and Ed Moses, who's the head of NIF, was present, and it kind of confused him. He considers LPI to be a very esoteric topic that like 6 people in the world understand. So he was kind of impressed that I could work through some of this stuff. He actually said to me, those are his words, "What are you?" Kind of an odd thing to get from someone who's so important. He knew I was in the computation directorate, but I think it kind of confused him that I could speak to the physics and I could speak to the math and the computer science. Of course, we all know this. We all know that computational science is sitting here in that intersection where all these fields come together. And unfortunately, not everyone knows that. But that's what's really special about this program and really special about the type of work that we all can do. So how many Slashdot readers do I have out there? 2? No, it's got to be more than 2, 3. All right. So you recognize this meme. I am not a plasma physicist. So take everything I say with a grain of salt. But I threw up here, I was trying to demonstrate, if you're like me, and I suspect many of you are, you have very broad interests. And, maybe it's not so bad as oh, look at that shiny object over there, that you can't focus. But certainly throughout my career, through all of my undergraduate and graduate training, and even past into my professional career, at any given time, I'm probably interested in some completely different thing and trying to figure that out. And so, I've kind of been doing this Brownian motion random walk through all these different domain areas. But it's really kind of interesting, right? Because I never planned to be here where I am. This isn't specifically what I intended to do. It feels right. It certainly is, I think, where I'm supposed to be. But this is not where I set out to go, right? And I think that's probably true of most people, but I think it's really true of us. that with the skills that we're given by having the opportunity to take classes in other areas and have a much broader education, we're much more able to react to changes in things and to see new opportunities and to take hold of those. And so I suspect, especially for those of you who are just getting started in that stuff, as your career progresses, you're not going to end up where you wanted to go. But that's not a bad thing. Now, a challenge that you get from being a CSGF is that CSGF kind of makes these chimeras. Right? The chimera is the mythical Greek beast of part lion, part goat, part snake. Won't say which discipline corresponds to which. One thing that I've noticed is that it's really challenging because you kind of don't have a home. There's not really a unified community because we're all distributed out through a whole bunch of different discipline areas. And academically, it's kind of a hard fit sometimes. Academics are often very stovepipe, and if you don't fall within the way that they like to categorize people in your interdisciplinary, it's kind of hard. I always find it funny when I interact with physicists, they think I'm a computer scientist or a mathematician. When I interact with computer scientists, they think I'm a physicist. When I interact with applied mathematicians, they think I'm an engineer, right? So to all of these people, I am a chimera, right? And you might find that to be the case in your career too. But there's a lot of good things about that, right? You have endless opportunities to work on all kinds of problems. You don't have to be pigeonholed into one area. And I'll get to this a little bit more. You have a very important role to play in multidisciplinary teams. So what I would challenge you to do is embrace the opportunity to lead. I'll speak to this research at the labs. I can speak to that. I've been at the lab since I got out of the program, so I can't really say anything about anything else. But definitely at the labs, research is more and more interdisciplinary and computational. And what CSGF really prepares you for is to become this bridge. I think every project I've ever worked on, and I've worked on a bunch, I end up being that kind of person in the middle who can listen to the physicists and tell the computer scientists what they're saying, or the mathematicians, because I understand the language of the different areas. I understand sort of the culture and how they approach problems. And that's a very important skill to have. So in addition to all the skills that you bring, the technical skills of the algorithms and the physics and the math the computer science you often are the facilitator for all these collaborations. I often get confused. One of my coworkers, I often write notes. I like to write lots of notes because I can never remember anything. So whenever I'm working on something, I'm always keeping notes. And my one collaborator loves this. He always calls them Rosetta Stones because he can go to those and figure out what the issue is in the physics domain by the combination of the math and all the information that I'm writing down. I think it was also mentioned yesterday, maybe Margaret mentioned this, we also tend to transfer ideas. We'll take ideas, we'll pick them up from aerospace engineering, and we'll take them over here to plasma physics and use them to great advantage there. So we serve a very important role, and you will serve a very important role, and you should really take advantage of that. We can be the enablers and catalysts for a lot of really great interdisciplinary research. Okay, so I'm going to talk a bit about things that I've done over the last 10 years. I've written it into 3 acts so that I could kind of put a moral on the end of each one. So Act 1 plays well with others. I have 2 grade school kids, so somehow the report card seemed appropriate for this. So a practicum I had at Los Alamos led to a postdoc at Livermore. That makes perfect sense, right? Actually, the group that I was in at Los Alamos, some of them moved to Livermore, and this is the easiest job I ever got in my life because I got a call, I don't know, about 9 months before I was done, asking me, when are you going to be done? And I think within a month, I had already been out, interviewed, and had a job offer. So appreciate those practicums because they can really be a good source for future employment. At any rate, when I got there, I was working on a project for the Adaptive Laser Plasma Simulator, ALPS. So this was an attempt to take AMR technology, apply it to some of these LPI problems. It used a whole bunch of modern algorithms. It was using fast adaptive composite with multigrid. We were using high-resolution Godunov schemes. And from that work, we then moved on. We were collaborating at the time. We were working on that project kind of by ourselves, but we were constantly talking to the LPI physicists. And they had their own code, PF3D, which is what they were actually using to help design experiments for NIF. So the question that kind of came up was, how do we use the knowledge we had with ALPS to help them out, to improve their simulation capability? This is proof that I am not a manager yet. I put equations in. So hopefully this doesn't scare anyone here. Just briefly, this is basically your hydrodynamic system. It's the Euler equations more or less with, this is that ponderomotive force I was talking about. So you have a force that goes like the gradient of the intensity. You couple that as your model. This is a fluid model of the plasma. This paraxial light equation, how do you get that? Well, Maxwell's equations are what govern electromagnetic propagation. You can take that, you can write it in that nice second-order wave equation form. You can do an approximate factorization of that. And you get these forward propagating and backward propagating, these weird operators that are complex, and it's actually hyperbolic. But they couple together. So here you have the laser intensity driving as a source for the plasma. And down here you have the index of refraction, for instance, which is tied to the density of the plasma. So the laser light sees the density in response to that. The electrons see this ponderomotive force and get pushed out of the way. We showed a lot of things with this code. It was 2D and 3D. We used this high-resolution Godunov scheme with corner transport upwind. We had that paraxial laser model, which was kind of cool because it was a sequence of lower dimensional calculations. You could start on the left and sweep across, because what you did was you only took half of the wave equation. You have a laser, it's propagating that way. Why would you solve the backwards stuff, right? So you'd solve along each plane. So on each plane, you had that sort of initial condition, but then it was basically a steady state calculation on each plane, and you just marched yourself across the domain. This is all built on top of the Samurai AMR library, and it was fully parallel, all the great things that we do. We could show for certain problems, a lot of AMR, the thing with AMR is AMR really works well if you've got a lower dimensional feature somewhere in your higher dimensional domain. Generally, you could get AMR to work well if you're doing like a whole beam calculation, because you have to propagate this small beam through a large volume. In some of the more, the physics calculations the physicists were doing, they're much more interested in sub-beam physics, and so in those situations, it's kind of like turbulence. You'd never use AMR for turbulence. Everything would be refined. But we were, for certain types of problems, able to get a reasonable speed up. What kind of drug it down, this laser integrator solve, because it was a lower dimensional solve, you don't get as much gain out of that, so that kind of held us back. But if you were here 10 years ago, you would have seen this movie, because I showed this 10 years ago. What's happening here is the laser propagates in, it pushes the plasma out of the way, focuses down on itself, and enters this catastrophic mode of filamentation, where it creates this really complex density field and starts scattering all over the place off of it. And so this was all done with AMR, and this is just showing you sort of where those patches of AMR lived and how they progressed through the simulation. All right. So what could we do with ALPS once we had it? Well, one of the things we did was we investigated this cross-beam transfer, and at the same time, there were some experiments using the Omega facility at Rochester looking at the exact same problem. And so we did a lot of work on that with them, trying to understand what this all meant for NIF. Because in NIF, you have these laser entry holes, and you can see there's these big cones of beams coming in. There's actually two cones. There's an inner cone and an outer cone, and the cones actually cross over each other. The difficulty is that once you start creating a plasma in here, it comes shooting out of these laser entry holes like a jet. Right? And so you actually get the conditions around the laser entry hole that you don't want, because it's the condition where you can exchange energy between the two beams. And the name of the game here is to irradiate the inside of this whole realm in such a way that you create this uniform X-ray bath. This is really just an X-ray oven. And if you don't get a nice uniform bath in there, you don't get a symmetric heating of the fuel, and it doesn't implode nicely. So they were really concerned about this. And one of the things that we learned from that affected the program was they made sure they had enough margin in the machine that they could slightly adjust the frequencies of the lasers between the inner cone and the outer cone that would detune this resonance. Now the irony of this, of course, is that they now are working on some designs that take advantage of this. Because you can send the energy, if you can control this, you can actually put more energy into one set of beams and have it scatter over to the other beam, and so you could actually get more energy on the one set of beams without having to go through all of the laser optics, which is one of the challenges. So they've actually taken this lemon and made lemonade. They've found a way to take it to actually improve some of their designs. All right, so I talked a lot about ALPS. What about this code that the physicists had? Well, you know, AMR isn't something that you can just plop into a code, right? AMR involves a lot of data structures. It really rips out the heart of a code, and you have to redo it. And they already had something working. It was based on an AL algorithm that they always ran in an Eulerian mode. And it had a lot more complicated physics. They did those light sweeps both forward and backwards to take care of different types of instability. So they had explicit models for these stimulated Brillouin, stimulated Raman scattering features. They had realistic beam profiles. So as you can see down here, they actually don't have a nice, clean, smooth beam, and they do that on purpose. This is actually one of their mechanisms to try and get rid of the filamentation problem. Because what they get is they get a lot of little hot spots that focus down, but they don't have one big catastrophic hot spot that causes the beam to just flail all over the place. And then they have a whole bunch of other models that are just kind of added on that try and mock up some of the non-equilibrium kinetic effects that you can't have or represent properly in a fluid plasma model. So these are kind of like subgrid models. So two of the things that we did was we actually added a multi-level multi-grid solver for them when they said, hey, you know what, we really need a better heat transfer mechanism in here. We want to study some problems. We want to be able to do electron thermal transport. And we said, okay, we can do that, and we're going to give you some nice stuff for that. They also said, well, you know, we want to do some of these calculations inside the whole realm. The whole realm is a multi-material flow. You've got a high Z material for the whole realm walls. You've got low Z material for the target itself. Sometimes they fill the whole realm with gases. So they needed something that would work, a fluid solver that would work on multi-materials. And I took advantage of that opportunity to give them a new multi-fluid Godunov solver. So one of the cool things about the heat conduction stuff, you know, it's got all the, you know, fun numerics like, you know, Newton iteration and you know, multi-grid with red-black Gauss-Seidel and fast adaptive composite. Well, why do we have fast adaptive composite? Well, they're used to calculating on these boxes that are really tight on the beam. And the reason for that is that they can't get enough resolution. So what we did was we took some of the technology that we knew from AMR. Now, this isn't AMR, but we took some of the technology. We actually did a dual calculation where we embedded their calculation inside a much larger, coarser grid so that we could push those boundaries way out and then apply suitable boundary conditions out here so it wouldn't affect the inside so much, so they could actually propagate the heat off of their computational domain. And this is important because they were at that time trying to do a series of calculations where they were looking at how the plasma would heat up as the laser was fired into it. And as part of that, they were trying to understand what beam conditioning techniques they should use, how they should make that beam all irregular so that it was most effective. In order to do those calculations, they needed to do this type of heat conduction problem, but they needed to get the heat off of their domain. So, you know, we worked on that, and this is actually a result of the calculation, and if I hadn't drawn that box in there, you wouldn't be able to tell, at least to the eye, that there were two calculations going on, and we were doing this fast adaptive composite scheme to keep everything in sync. This was pretty cool stuff. So they ended up doing these. They did some experiments on NIF. They made heavy use of the Spitzer-Harm heat conduction that we gave them. And at the time, you know, this is a bunch of years ago, at the time, these are some really big calculations for what they were doing. And what they found was they had a couple different treatments, and some of those treatments didn't work very well. As you propagated this laser in, it would, between the heating and the focusing, you would get this filamentation still. And because of that, the plasma couldn't punch through, or the laser couldn't punch through the plasma. So because of this, it allowed them to figure out sort of which techniques they should use when they finally would get around to firing the full NIF to try and get a beam condition so that they could get it deep into the whole realm. We couldn't do these calculations in 3D because we could only get about 100 picoseconds in, and we needed to go for more than a nanosecond. So we did some tricks where we did some 2D calculations and then kind of did a similarity type thing saying, well, how would this look in 3D? Because energy goes in a different, propagates differently in 3D than it does in 2D. But we could reproduce the laser transmission trends that they were getting out of the experiments at the time. And the cool thing about this was we got a Nature Physics article out of that. I never in my life expected to publish in that journal. So that was kind of cool. I added a pretty simple volume fraction model with this complicated Godunov solver, which is frankly better than the hydro solver that they had in their code. Because they would do these radiation hydrodynamic calculations and get the interior of the hole round that looks like this. And you've got all this blow off from all this ablation going on. And they're trying to propagate a beam in this way. And so it's going through a whole bunch of different materials. So that was basically a single shot of just, I put that solver in for them, and they've used it ever since. They liked it so much. Just give you a sense of what that kind of looks like. So this is just a density field. So you see the laser propagating in. You can see it's all ratty because that's how they like it. But these are the stimulated, I think the right one is stimulated Raman and the left one is the stimulated Rowan. So this is energy that is, you're getting these resonant conditions between the interaction of the laser and the plasma because you get just the right conditions at those points. And it's actually reflecting the energy directly back. And this is actually one of the worst case scenarios because they don't want energy to go back into the optics that they have. They're already running the optics fairly close to what they can afford to do. You get more energy in there, they'll start destroying things. So this is actually, they make a lot of use of this multi-fluid solver now. Why is it not going? Go. Hello? Stuck. Interesting. Gotta love Windows. There we go. Okay. So, okay, that was a long story of a lot of different things. What can I say about that? What lesson could you take away from that? The one thing I would say to you to learn from this is lead by example. Don't be dogmatic. I know we all have our favorite schemes. Right? But you need to be agnostic about this stuff. At the end of the day, there really aren't any absolutes. And methods, techniques that you use, the models that you use, they're just tools. And for a certain type of problem, there will be better tools and worse tools. It's seldom the case that there's a right tool. So be open to options and don't automatically go in and tell people that, oh, well, you're just solving this wrong. This is the method you want to use. You don't want to do that. Particularly since you might come into it and be working with domain scientists, and maybe they're not a numerical analyst, or have had formal training in that. But these are smart people, and they come up with some pretty innovative schemes. And often, if you look at the heart of the methods that they develop, there's some gems in there of information that you might want to use. So they have a lot of insight, and definitely, you shouldn't be like a bull in a china shop if you're going to be collaborating with people in another discipline. As Eisenhower said, you don't lead by hitting people over the head. That's assault, not leadership. So approach people in other domains when you're in these interdisciplinary teams with a little bit of humility and some respect, and it'll make your collaboration go a lot better. The other thing that works really well is get your hands dirty. One of the things that some physicists I know really hate is when the applied mathematician comes swooping in and says, we're going to solve your problem. Tell me about your problem. This is our problem. Okay. I'm going to idealize it away this way. And I'm going to solve that problem. And I'm never going to come back and talk to you again and help you. Right? They really hate that. The one thing they do really like is you come in there and say, you know what? I think I've got some things that will help you. And I am willing to roll up my sleeves and get in your code and implement it for you. Right? You do that. You might have to hold your nose. It might be spaghetti Fortran that you're working with, but it often is. If you do that, you gain a lot of respect. And if you deliver, if you actually provide the increased benefits that you promised, that gives you a lot of capital. And they'll come back to you. And the next day, if you just suggest something, say, why don't we try this? They are more than likely to say, sure, go ahead. That's a great way to try and get new ideas and new technology into sort of existing codes, into existing programs. All right, moving on. Act 2. Adjust easily to new situations. All right, so I told you about some ICF stuff that I did. Based on that work, we had a lot of collaborations, and so we were approached. There was a desire to build an edge plasma code. This sounded cool at the time. It is cool. It's also hard. So you have this tokamak, right? You've got these magnetic fields. This actually shows you a specific separatrix flux surface in the tokamak. The stuff on the inside is what they consider the core. That's the actual confined stuff. The stuff on the outside is plasma that escapes and can go off and hit the walls. What's of interest here is that a very special thing happens in tokamaks where there's this H mode, where H stands for high confinement, where you can actually get this really steep gradient that forms called the pedestal that keeps all the plasma in that center. And they really, really want to operate in that regime. Unfortunately, they don't know why it forms or why it falls apart. There's all kinds of disruption mechanisms. So that regime is really great because it forms a natural transport barrier. And they want to keep all the energy in the center. So that pedestal helps keep the energy flowing out and getting out to the walls, getting off to the diverter plates. There are methods for solving the core. There's lots of methods for solving the core. People have been working on the core very hard for a very long time. The extension of those methods to the edge, though, is a little bit problematic because a lot of the assumptions that went into the core totally break down when you get out to the edge. You'll notice that the density drops off dramatically. The temperature drops off dramatically. The plasma out here, out near the wall, is really collisional. And the plasma in the core, you can basically ignore collisions. There's also a huge difference in terms of the equilibrium aspects of these flows. And so often what you can get by with in the core is to do some kind of perturbation technique and do something called a delta F code, where you're just doing a perturbation for a Maxwellian. I can't do that in the edge. So how do we do this? Well, we have these things called gyrokinetic models. Kinetic model, you describe your plasma as particles. There's kind of two ways to do that. You can do it directly, just discretizing particles and evolving those. It's a very time-honored method that works pretty well. The other way is to use a distribution function. And so you basically say, I've got this continuous function of time and space and velocity that represents, at a given point in space, I've got this distribution of particles with these velocities at this time. So you could evolve that directly, too. Now, the problem with this is that, if you're in 3 dimensions, this becomes a 6-dimensional thing that you have to solve for. And the motion is very complicated. Charged particle moving through an electromagnetic field spirals. That's not an easy motion to describe. And it's also extremely fast. So one of the tricks that they use is this gyro averaging. This is how you get to gyrokinetic equations. That motion is so fast, it's effectively as if you had a ring propagating through. So instead of thinking this as a particle doing this, you can think of it as a ring of charge just kind of sliding along the magnetic field lines. That solves 2 problems. You get from 6D down to 5D. Yay! Doesn't sound like much, but it means something. It also takes out that fast gyro frequency that is a fast time scale that you really don't care about. So that's sort of one of those wins of changing the mathematical model before you even start discretizing. So a lot of work has been done on this in the core. The plasma edge differs from the core. There's a different ordering. These are asymptotic expansions, and there's a different ordering that you need. Actually, one of the challenges with that is that no one agrees on what that ordering is. So you take the equations that you think are the best ones. And so if you do this, the continuum advantage is that it doesn't have noise. When you do the particle methods are great because you can sort of undersample the phase space. And so the problem doesn't scale as fast. The downside is that it's noisy. If that matters to you, that's a problem. And the noise doesn't go away very fast, right? It's like a 1 over into the 1/2. Another problem with the particle codes is that this is a highly collisional regime, which is an extremely expensive calculation to do with particles. The continuum side, however, it's not like our collision operator is pleasant, but it's not nearly as expensive. And there is no noise, so you can control the error better. The downside is you got to lay down a grid in phase space, right? And so the size of that problem grows geometrically with dimension, right? Equations, yay. So these are the equations you get. All this really says is this is for a particular variable. This is just advection of this distribution through phase space. That's all that really is. And this was the Poisson equation at one point before I did the gyro average was done. Okay, so you basically have this coupled system. You've got this hyperbolic propagation system. You've got this elliptic gyrokinetic solve. And what's complicated about it is this R. You actually want to solve on these magnetic field lines. There's a lot of gain to doing that. It's kind of like discretizing along streamlines. You can use a lot less discretization points if you kind of follow the actual streamlines in the flow. So that the real complication with this is solving in this unbelievably complicated coordinate system. How do we go about doing that? Well, so we've been working on this project with Phil Colella and Dan, wherever he is. Dan, there he is. So we came up with this formalism. We wanted to use finite volume methods because we're concerned about particle conservation. So we came up with this way of expressing finite volumes on this map grid. It's not really the way you usually do it. With finite volumes, usually you can do everything geometrically. And you calculate surface areas and outward normals and that kind of stuff. We want everything to be high order, primarily because high order buys us a little bit in terms of needing fewer grid points in this higher dimensional space. So we came up with this way of extending finite volume schemes in a systematic way to doing, say, fourth order or any other order that you want that has some nice properties about it, one of which is that it preserves the free stream, which is just, of course, it's a nice property to have, but in some sense, it's a measure of the stability of your scheme. That's probably all you really care about seeing about that. The geometry we solve on then is, so this is sort of an example, a cartoon of what this edge looks like. So we have to solve a little bit inside that separatrix and a little bit outside that separatrix. You can actually take this and map it to that set of rectangular grids, and that's what we want to do. Now this is interesting. It's got these two singular cuts in it. We've got this odd point down here called the X point. The key here is we can do this with a map multiblock technology. This is something that has been done in the aerospace community for a long time, typically at second order, but it's been done for a long time. The challenge is, in order for all this formalism to work, it relies on a fundamental assumption that you have smoothness in your mapping, right? This is decidedly not a smooth point. This is a nice discontinuous point for derivatives and whatnot. So the trick to get around this, and this is actually working, we have this in a working code now, to fourth order is, we go between the blocks and we have these go cells, and to fill the go cells, we actually don't force these mapped grid lines to line up anymore. We just do a smooth, continuous extension of the mapping off of our block. So it doesn't line up with anything, but it's still differentiable. And then to fill those go cells, you use a least squares process to try and figure out what value to put in the go cell. Some of the other challenges with this, so we've developed this code called COGENT, which is a sort of an inside joke, because the original code we wrote was called Tempest. And Tempest was written as we were learning this process, the physics that was involved. And it wasn't really the best designed code, because we kind of learned it piece by piece of, oh, we got to add this physics now. It's like, oh, well, that changes everything. I wish we'd done that before. So Tempest wasn't the best code because we had optimized for the wrong problem because we started at the wrong place. And so when we got far enough along and realized, okay, now we know how to do this, we decided to write COGENT. And so this is actually built on Chambo, which is a different AMR infrastructure, using all these locally rectangular grids. It's got all of this fourth order map grid technology built into it, so it's nice and easy to work with now. One of the challenges that's kind of interesting is, again, this working between multiple dimensions. We have this distribution function which we're trying to propagate. Right now we're doing 4D and 2D. So we're trying to propagate this distribution function in 4D, but these two equations are coupled. We need to get a density out. You get the density out by integrating over all the velocity. So you drop from 4 dimensions down to 2 dimensions, right? Then you do your field solve in 2D, and then you have to inject that back up into 4 dimensions because that's going to accelerate the particles, the electric field that you get out of that. And then the Vlasov integration is on 4D. So you have this going back down and back up, and it's challenging to get this to balance well because the size of the work is quite different between 4D and 2D. COGENT's still a work in progress. Some of the things we have shown, we've done this standard test case of geodesic acoustic modes. They're not very interesting to look at. But we do get very good agreement, certainly better agreement than we got with Tempest, which is these black points, with the sort of asymptotic theory that you can derive, which was nice. I mean, we kind of suspected that Tempest wasn't going to do as good a job, but it really impressed the physicists that we were working with. Okay. Really? Wow. All right. It converges at fourth order. All right, so interesting thing happened with this is because I did all this work, I also been doing some work for verification for some of the programs that didn't go unnoticed, and I was recommended to work on this fusion simulation program. So this is a national level thing. The idea is the fusion community has all these codes. What they want is an integrated simulation capability. They want to be able to actually simulate a tokamak, and they've got core codes and edge codes and RF codes, and they want to put all this stuff together. So there's been this 2-year planning process of trying to figure out, well, how do you structure a program at $25 million a year for the next 15 years to do that? And I've had the opportunity and privilege to serve on that. And because of the stuff that I know, I've basically been leading the verification UQ portions of that plan. So let's talk about success. Yeah, that is me. So some success is really easy to measure, right? Either there's a puck in the back of the net or there's not. Our careers are not so easily measured, right? We have our standard professional metrics, right? Oh, you're publishing papers, you're on that editorial board, you're doing community service. Those are more of those binary measures. You either have them or you don't. But I think really the more meaningful form of success is that others seek out and rely upon your opinion. That's when I think you really know you've had success. And the cool thing about that is you then have the opportunity to influence directions of research and directions for programs. And I think every single one of you out there, because of the nature of the fact that you're in this program and you're being trained the way you are, will have that opportunity. And I think that's a really great quote from a former Wolverine. And it's very appropriate for this group, right? Because most of us are just painful overachievers, right? All right. I'm going to run with scissors through this because I'm running out of time. So I got the opportunity to lead my own research team of physicists and mathematicians and computer scientists. This was sort of a step back from the work we were doing at Gyrokinetics. We wanted to do kinetic simulation for LPI. And the approach was to use high-order Eulerian methods, which isn't the way it's normally done. They usually use semi-Lagrangian methods. Finite volume formulation. We were trying to use these higher-order methods and also AMR to try and reduce the cost in phase space. With some added features, they don't like oscillations and things like that that you get from very steep features, and so we had positivity preservation included and control of unphysical oscillations. This is very similar to the equations that we were solving before. It's a little bit simpler now because I don't have to deal with the magnetic field that's sitting there. So this is just the Vlasov equation, which is a transport equation in phase space, coupled to a Poisson equation. The stuff I'm going to show is all on this periodic domain. Finite volume formulation, as I was talking about before, we're using these high-order fluxes that take into account, when you go to high order, if you go above second order with finite volume, you have to be very careful. You have to be very careful about what's a cell average, what's a face average, what's a point value. If you're very careful about doing that, you get the fourth order face average is an expression that kind of looks like this. How do I formulate a fourth order face average in terms of the product of two fourth order face averages? We've worked all that out, used a standard Runge-Kutta to integrate that. We could show that this new scheme that we have, it's kind of based off of Wino. I think you heard about Wino yesterday, so I'm not going to introduce that. But the new scheme performs very well. It's much less dissipative, which is exactly what we wanted. And we were able to do some physics with this code. In 4D, we were able to show some things about wave bowing, which the physicists were interested in, which is an effect that has to do with nonlinear trapping of particles. So what is nonlinear trapping of particles? Let me show you what that looks like. I won't go through this slide. This isn't much fun. It's just, I had to do a lot of work to get 4D to talk to 2D, okay? It's a non-trivial thing when you have an AMR mesh, and you've got multiple levels on top of each other. But you have to do these integrals to get the information down and then put the information back up. So I had to do a lot of work and figure out an algorithm that actually scaled well to do this. I eventually got it, but I won't bore you with the details because I want to show you a movie. Movies are more fun. So this is an example of the bump on tail instability. And on the left, well, on the left is the solution. On the right should be the grid adaptation that goes with it. I'll let you watch the solution, then I'll see if I can't get the movie on the right to work. Get out of there. Let's try this again. All right, so now you can watch how the meshes move. There we go. So one of the cool things about this is that you can actually use these long stretched out cells at the top and the bottom, which buys you something in terms of stability because this is a velocity. And so the further out you go, the smaller your time step has to be. So the fact that I can put this coarse mesh down is actually a big help. But you can see how we're picking up the spiral of that feature. What that is the particles in a resonant interaction getting trapped. There's a potential well basically propagating along that gets formed by a slight perturbation early in the solution. And the particles that are at just the right velocity get stuck in that potential well and can't get out and start spiraling around. And that causes a form of damping known as Landau damping. All right, so I'm almost done here. What did I learn from that? What did I learn about leading this team? Give people freedom. You know, you need to guide your team to get your stuff done, but you can learn so much if you give them a long leash and let them run, because they'll come up with things that you never even thought of. You can't anticipate everything. You need to really leverage other people's ideas. If you're passionate and you've got a plan, you can get really good people, and that's important. That's why these are all sharp pencils. You want sharp people working for you. And you have to understand how people work and how to motivate them. Not everyone works the same way. What makes you go doesn't make other people go. Focus on your goals. Be proactive. Don't put things off if you know there's going to be a problem. Get on it right away. And surround yourself with sharp people so you can trust their opinion. You don't want to second guess everything or micromanage. You've got a team, rely on them. All right, so congratulations to CSGF. I definitely would not be here without this fellowship, and I thank CSGF for that. And let's hope that CSGF, the end of CSGF is 20 years away, and it always will be.